Today we're going to continue with some more properties of matrices, in particular considering a matrix product. In general, the product of an n by m matrix A, which consists of elements aij, and an m by l matrix B, which consists of elements bij, is defined to be the n by l matrix AB is equal to C, where Cij is defined as the sum from 1 to m of aik bkj. So column J of the product matrix AB is equal to C is the column vector Cj is equal to A times Bj, where Bj is the jth column vector of the matrix B, and rho j of the product matrix AB is equal to C is the row vector Cj transpose is equal to Aj transpose times B, where Aj transpose is the jth row of the matrix A. These matrices can only be multiplied to yield a product when the number of columns of the matrix A is equal to the number of rows of the matrix B, and the number of rows of the product AB is the number of rows of A, while the number of columns of the product AB is the number of columns of the matrix B. As an example, this 2 by 3 by 3 by 2 gives you a 2 by 2 matrix. And you can calculate each of these elements explicitly. For instance, C11 is equal to A11 B11 plus A12 B21 plus A13 B31. If you follow my math, you see that for instance, if you see the C22 matrix will be the second row times the second column multiplied and added pairwise. You can check pretty easily that the matrix product is associative in the sense that A times B times C is equal to AB times C, and consequently multiple products are well defined. Additionally, you can tell that it's distributive in the sense that A times B plus C is equal to AB plus BC, and A plus B times C is equal to AC plus BC. It is worth calculating a few of these to become familiar with the technique. We now move on to a proof, which says that if a linear transformation T from Fn to Fm is described by an m by n matrix B, and a transformation S from Fm to Fl is described by a L by m matrix A, then the composition S of T from Fn to Fl is described by the product matrix AB. For any index between 1 and n, let's look at S of T of delta I, since we know that every linear transformation is defined by how it acts on the basis elements of the initial space, and we see that delta I from 1 to n form a basis of f to the n. Therefore, we'll check what S of T of delta I is. Well, of course, by definition, that's S of T of delta I, but T of delta I, we'll note that T is represented by a matrix B, therefore we can write this as this explicit sum over the bki's of delta k from 1 to m for all the deltas. Next, we apply the linearity of S to get this to move it inside the sum and pull out the scalar factor of bki, so the sum from 1 to m of bki S of delta k. Well, we also know the definition of writing S of delta k. We can write that explicitly as a sum over the A entries from 1 to L of ajk times delta j. Since first you should note that delta I has been transformed to an output in delta k, so delta k serves as a basis of f to the m, while delta j will serve as a basis of f to the l, because you are still transforming them, but you're taking linear combinations of those transform vectors. We take the sum and then apply the properties of sums to pull this into a double sum of the sum of ajk delta ki. However, if we remember our definition of the product matrix, we can write each of these entries as a sum over some elements, namely of this sum from 1 to m of ajk bki. Each of those terms is cji, so we're simply taking the same sum from 1 to L of cji, namely of delta j, that is a linear combination of the delta j's. Thus, this composition is described by the matrix C is equal to cji, where cji is described in this way, so that C is equal to AB. This suffices for the proof. Next time, we're going to consider some ideas about invertible versus non-invertible matrices, and we'll derive some interesting results, particularly related to the abstract algebra we did before. Thank you for watching.